Hi guys, welcome to this video on Redshift. So this is part of P8, which is the space topic for separate science. So what we're going to look at is, first off, what this thing called the Doppler effect is. It's not technically in the specification, but if you know what the Doppler effect is, if you understand it, it's easier to apply it to what Redshift is. We're then going to look at what Redshift is. We're going to explain why it occurs. We're going to look at the different factors that affect Redshift. So to start off with, if we talk about waves, so if you remember, waves have two properties we need to know about, which is their wavelength and frequency. So the wavelength is the length of one whole wave. So you could say it's the distance from peak to peak, trough to trough, or the start of one wave, the start of another wave. And the frequency is how many waves there are per second, how many whole wavelengths pass a point per second, or how many oscillations there are every second. So if you look at these two different waves here, the wave at the bottom has a longer wavelength. And if you're keeping the speed of the wave the same, they're inversely proportional. So the wavelength is inversely proportional to the frequency. So if you increase the frequency, you're decreasing the wavelength. In this case, because I've increased the wavelength on the bottom one, it means that the frequency of the wave is also lower. So if we look at this thing called the Doppler effect, now the Doppler effect you would probably observe in everyday life. You may have seen this in things like sirens, anything with a siren going past you, or something like a racing car going past you. It is where there is an apparent change in frequency or wavelength, what's frequency and wavelength of a wave. Now, this is due to relative motion. So, for example, you'll see videos of this on YouTube if you type in Doppler effect fire engine. If you have a fire engine with its siren going past you, you will notice that it sounds higher pitch as it's coming towards you and lower pitch as it's moving away from you. So why is that? Well, that must mean if it's a higher pitch, it's a higher frequency coming towards us and a lower frequency moving away from us. Now, that's not because the person on board the fire engine is changing the sound wave in any way. It's due to this relative movement. So it's due to the fire engine moving towards and away from you. It could also be the opposite. So if the fire engine was stationary and you were driving past the fire engine, it's the movement from observer to source as well as source to observer. So now I'm going to show you a quick clip on why exactly this effect happens, called the Doppler effect. So if you take this for example, so this is a sound source that's currently not moving, and the observer we're saying is not moving either. These red waves here are the sound waves that are being emitted by the sound source, and if you look, they're coming out as concentric circles. Now the distance between each red circle is the wavelength. So if you can see from all the way around this sound source, the wavelength and hence the frequency is the same. So because the sound source and the observer are stationary, there's no relative movement, wherever the observer is, they will notice no change in the wavelength frequency. It will sound exactly as it should be coming out of the sound source. So in this clip, we've got the source now moving relative to the observer. So if we say the observer is somewhere down here, as you can see, it's emitting the sound waves at the same frequency, but because it's moving this way, it's catching up with the sound waves as it produces them. So it's squashing them together. Therefore, the wavelength is shorter than the original, and the frequency is now higher. And if you look on the other side, because it's moving away from the sound waves that it's making, these sound waves are getting stretched apart, the wavelength's increasing, and therefore the frequency is decreasing. So if we look at it from an observer point of view, let's say an observer is where the mouse is. Right now it's getting sound waves of a higher frequency because the sound source is moving towards the observer. But as soon as it moves away from it, it's now getting the lower waves, the lower frequency waves. So you can get an apparent change in frequency depending on the motion of the observer and the sound source. What happens if you increase the relative velocity of the sound source compared to the observer? You'll see that because they're moving even faster, these waves are getting even more bunched together. Therefore, the frequency is increasing even more, the wavelength is decreasing even further too. Okay, so now that we've looked at what the Doppler effect is, now we want to apply this to redshift. So if we go back a step, if we look at white light is from the visible spectrum. It's made up of 7 different colors: RO, Y, GBIV, red, orange, yellow, green, blue, indigo, violet. Now, the reason why you have these different colors is because they have different wavelengths and they have different frequencies. So red has the longest wavelength and the lowest frequency. Violet has the highest frequency and the shortest wavelength. Now, you can get this thing called an absorption spectrum. So this is an absorption spectrum. And if you look at it, it looks like all of the colors from this white light visible spectrum, but there are some black lines there. Now what happens is if you have white light, all the colors from the visible light spectrum shining through an object, then some of the atoms will absorb certain frequencies of light. In fact, what's actually absorbing the light are the electrons. So in this case, you'll see that you've got some violet light here, a bit of blue, looks like we're sort of going to green there, and sort of reddy orange. All of these different frequencies are different light energies that are absorbed by electrons in atoms. And what happens is that when the electrons absorb these certain frequencies, they'll make transitions in their shells, they'll move up. So what's happening is that only these certain frequencies have been absorbed and the rest are just carrying on. So when we look at light from galaxies and stars, we're only looking at the bits that haven't been absorbed. Now this is quite useful because what we can do is we can identify what elements stars are made up of because of this, because certain elements always absorb the same frequencies, which is how we know things like the basic stars are made of hydrogen and helium because they always absorb these certain frequencies no matter where you are in the universe. If we go back to the Doppler effect, we said the Doppler effect is where there's an observed change in wavelength and frequency of a wave depending on the relative motion. Now, if we apply that to light, it's exactly the same thing. We said earlier with a fire engine, when the fire engine's got its sirens on and it's moving towards you, it sounds higher, and when it's moving away from you, it sounds lower. The same works for light. Now, obviously, light's a bit different because you can't hear it, you can only see it. So if we have something like a galaxy or a star that's moving away from us, same thing is going to happen. The light that's been emitted from it is going to stretch, just like it is in this little animation here. So because it's stretching, the wavelength is getting longer. And instead of it, like a fire engine moving away, sounding lower, it looks a lower frequency. And if we go back to Hiss, you can see that the lower frequencies are things like red. So this is where we get this term redshift from. When you have galaxies or light sources or stars and even that are moving away from us, their light appears redder than normal. Now all that means is that the light that we receive from it is a longer wavelength than actually is being emitted. You can also get the converse as well. You can get blue shift, which is where if you get galaxies or stars moving towards you, the frequency is increasing and therefore it appears bluer. Now, this is probably not the right term to use, appearing redder and appearing bluer, because what's actually happening is if we look at the absorption spectra, if you look at these two here, you will see that the bottom one is the original absorption spectra we're getting from this galaxy, and the top one is one that's been redshifted, and you can see that those lines, those black lines there, are all moving. So what we say is that the spectrum is shifting towards the red end, i.e. the wavelengths of light that we're receiving are now all appearing longer and they're all moving towards that end. It's not to say that all the light's going to appear red, it's just that all of them are shifting towards the right end of this spectrum, which happens to be red. Now, with redshift, it only happens when you're moving close to the speed of the wave. So with something like the Doppler effect with the sound, it's very easy to notice it because sound's only 330 meters a second. So a car, it's not moving close to the speed of sound, but it's not miles and miles away. So you won't notice redshift if you're going quite slowly, if you've got someone running with a torch. It has to be moving very, very close to the speed of light, 3 times 10 to the 8 meters a second. So what does this all mean? What is redshift? Well, as I said, it's where galaxies or light sources are moving away from us and their wavelengths are increasing, and you could say the spectrum is shifting towards the red end. And why is this important? Well, when we look at all the galaxies around us, they are all appearing red. They're all having their spectrum shifted towards the red end of the spectrum. So what's causing it? Well, this is where we get on to our next lesson on the Big Bang. we believe that the universe is expanding, and because everything is moving away from everything, we think that that's caused by the universe expanding. But that is for another time. Okay, right guys, hopefully that's helped. Enjoy, see you next time.